So Ved just asked me a question, can people interrupt me with questions? And the answer is yes. If you get a microphone, that's great. If not, I will repeat the question so it's recorded for posterity. Thermal convection is the engine that powers geological activity. And on the Earth, the most obvious manifestation of thermal convection in the interior is the operation and existence of plate tectonics. This is Geodynamics 1, the basics of thermal convection. We have three goals today. The first is an introduction to the governing equations, and I will try and derive at least two of them for you. Second, why does convection occur? To do this, we will understand how we transition from a planet that transfers heat by conduction to one that undergoes thermal convection. And to end, and very briefly, I'll outline some of the complications to this basic picture of thermal convection driven solely by variations of density produced by variations of temperature. And it's those complications, in fact, that produce the great richness and cause us problems that were highlighted in the two presentations you saw earlier this morning. Okay, we're shortened by about an hour, by 17 minutes, and so I will do what I can to stay on time because we have lunch next. First, though, it's good to ask, why are we bothering to do this? Why do we care about mantle convection and how the mantle flows? And can we keep the lights on? I'm going to use the blackboard, Quentin. Thank you. The equations that we will be deriving and looking at today provide the basis and a starting point for solving on a computer or analytically for the flow inside the Earth. Right? And we will use the solution to this flow and the insights from those equations to interpret observations that we obtain from seismology or constraints from mineral physics. You will see in Geodynamics 3 by Torsten how we can more formally integrate observations with these equations to say something about the inside of the Earth as well. Okay, so let's begin with this picture. This is an example of a computer simulation of mantle convection. It's a solution to the equations we will be deriving in just a minute. It's a cross-section through the Earth. The bottom is hot, the top is cold. If you heat up a fluid, it becomes less dense and it rises. If you cool a fluid, it becomes more dense and it sinks. Red is hot, blue is cold. You can see regions where the mantle is rising, places where it's sinking. Right? Very simple description of what we call thermal convection. And to leading order, this should characterize what goes on inside the Earth, where the inside is hot and the surface is cold. I am not Bruce Buffett. These lecture slides were prepared by Bruce Buffett, and regrettably, he entered the hospital this weekend. I think he's okay, but I have not heard an update, and so I'm presenting these slides and this topic on his behalf. So please bear with me. But on Earth, we have plate tectonics. Right, as a product of mantle convection. If we look around our solar system, in fact, we see different ways in which mantle convection operates and affects the surface. This is Jupiter's moon Io, the most volcanically active planet in our object in our solar system. Each of these things are places that have recently or are currently actively erupting. Rather than having plate tectonics, heat and mass is delivered directly to the surface. We see convection everywhere we look. Right. On the left is a rising cloud in the atmosphere. In the oceans, we have convection driven by variations of density. All convection is caused by variations of density, where the density changes originate from both changes in temperature as well as salinity. The contours you see here, I think, are differences in density relative to some mean density. This is a cross-section through the ocean. We see this layer of dense water sinking to the base of the ocean to drive and participate in the global ocean circulation. Convection in the sun. What you're seeing here is the influence of convection on Earth, on the magnetic field of the sun. These things are called granules. They're about 1,500 kilometers across. They last for 8 to 20 minutes, but convection once again. And the reason you have these three different pictures to go with the picture of mantle convection on Io earlier is that they're all manifestations of things going up because they're light, dense things sinking, but influenced to variable degrees by the importance of inertia, rotation, or magnetic fields. Geodynamics lecture number 4 is going to cover the effects of rotation. Geodynamics lecture number 6 will add to this magnetic fields. So they will worry only about balances, flows that represent a balance between buoyancy and viscous forces. And let me remind you to interrupt and ask questions anytime as you have them. And that includes about notation, questions about notation, the mathematics, or of course the physical concepts. So here's our objective for the next hour. including questions and discussions. We'll begin with a brief overview of the governing equations, their origin, and some of the approximations that go into them. I'll introduce you to the concept of a dimensionless number and why we care about them and what we use them for. And I will try and remember to keep a running list of the dimensionless numbers on the board. And there's a reason for that. Very briefly introduce to you how we determine whether a system should convect or not, a way of describing a convecting system with something called the boundary layer model, and how we apply these boundary layer models to think about thermal evolution. Okay, so let's start with an equation that describes conservation of mass. And the equations that describe convection, for all those pictures that I showed you earlier, including the mantle, is a set of equations that describe conservation of a number of fundamental quantities: conservation of mass, conservation of momentum, and conservation of energy. And thermal convection is the product of solving that set of equations. So let's begin with the statement of conservation of mass. We're going to imagine we have this blackboard's a big fluid, right? We've got some volume inside this fluid. I'll call it V. It's bounded by surface area S. And to characterize this surface, we'll define a quantity we call the unit normal vector n that's normal to that surface. And what does it mean by unit normal? It means that the dot product of the unit normal, or the magnitude of this unit normal vector, is equal to 1. Okay. So the statement of conservation of mass says that we're not going to create mass or destroy mass. This is a great approximation for what we care about. Some of you know E equals mc squared. That's a conversion of mass to energy. We will not worry about those complications. And to derive an equation that says how mass is conserved, let's take this volume and think about how much mass is leaving that volume at a given point on the surface. So let's pick a little surface here. Right. Why would mass be leaving that volume at that point? There's something else I need to draw in this picture. Right. We don't have a static blackboard, a static fluid. It's moving. Right. So we're going to have fluid moving through this region. In the notes that Bruce prepared, he uses the symbol V for velocity. If you see a U on the board by mistake, that's the same as V. Okay. So at this point here, are we going to have, do we have mass transferring, moving across that interface? We do, right? Because we have a speed, right? This fluid that's moving with speed, velocity V, is carrying mass across that interface. The mass flux per unit area is going to look like the density of the fluid moving across that surface times what? Times the velocity, right? That's telling us how fast mass is moving across that surface. Is that completely right? What happens if the velocity is perpendicular to the boundary? Parallel to the boundary. There's no mass flux, right? So the mass flux at any point is the dot product, right, the projection of the velocity onto the normal vector. Okay, so let's write down then the net flux of mass out of that volume V. And when I use the expression flux, that means mass per unit time per unit area. Net flux. Okay, so at any one point, right, the mass flux is rho v dot n, right? And if I'd like to know what the total is across out of this whole volume V, I just add up this flux all the way around the boundary, which is the same as integrating over that surface S. Okay. So that's how much mass we're losing or gaining, depending on the nature of that velocity field. If we have mass leaving this volume, what happens to the mass inside the volume? It has to go down, right? So the mass inside that volume is equal to, what's the total mass inside that volume? Mass is what? Volume times density, right? But our density can vary with respect to position inside this volume as well. So to determine what the mass is inside that volume, we're going to integrate density over that volume, right? That's the mass inside the volume. And if we'd like to know how it's changing with respect to time, Thank you. So we're going to integrate with respect to volume the density to get the mass. And this is a flux of mass, so how it's changing with respect to time. So we're going to be integrating the change of density with respect to time over that volume. And I'm going to put a minus sign in front of this integral. Why a minus sign? Right. If we're losing mass so that this is decreasing, the average density is going to change. Right? Okay. So that's very nice. It's a statement of conservation of mass. Any approximations or assumptions? We're the quietest group of people for a Monday morning ever. Density could be a function of time, right? We're taking a derivative with respect to time. It can vary in space. We've made absolutely no assumptions or approximations. So this is great. We have a statement of conservation of mass. It's a little bit ugly, right, in that we have an integral over a surface, we have an integral over a volume. But there's a useful trick, hopefully you've seen at some point. The integral of something, dot product a unit normal over a surface, can be converted using the divergence theorem into a volume integral. And so this equation here can be written as the integral over volume of the divergence of rho v dv. Well, this is very nice now because the left-hand side and the right-hand side are both integrals over volume. We haven't said anything about that makes this volume special. So the only way for this equation to hold, or this equality to hold, is if the right-hand side is equal to the left-hand side. We can put everything under one integral sign. And so this requires then that the derivative of density with respect to time plus the divergence of density times velocity is equal to 0. Right? To go back from here to this equation, you just integrate over volume. Okay. And this equation is called the continuity equation. And it's a statement of a conservation of mass with absolutely no approximations or assumptions. Okay. A couple special limits of this equation, though, that will become relevant. If density is in fact constant, what happens to the first term? It's 0. I can take density outside of the derivative sign, divide both sides by density, and this becomes a much simpler equation. It's the divergence of velocity equals 0. Right? So we're running out of space on this board, but if density is equal to a constant, then the divergence of velocity is equal to 0. Okay. And so this is one way, in fact, to think about what the divergence means, right? It's basically a statement of what goes in is equal to what comes out. Okay, and so this is our first equation, a statement of conservation of mass. Questions? Okay, so next we have...
So in continuity, traditionally people neglect the variation of, say, density with temperature.
Okay, so...
I mean, you put that back into momentum equation.
The question is, we've neglected here how density may vary with temperature or composition or all kinds of other things. We have actually made no assumptions about the nature of how density varies, what causes it to change. There will have to be other equations, an equation of state that relates density to temperature, to pressure, and those will appear later when we start worrying about what it is that governs density. But as a statement right there, I think we've made absolutely no approximations. Okay. Let me get the blackboard. Okay. Okay, so Bruce made these lovely slides called some tools. There are a variety of mathematical tools or definitions that are quite useful for understanding these equations and deriving them. We'll make use of these, and so let me talk you through what they are. First will be an introduction to something called the material derivative, a derivative in a moving reference frame. So let's imagine we have some mass inscribed inside this shape here, right? And it's immersed in a flow field indicated by these dotted lines that's moving. And we're going to take this mass and move it along with that flow. Right? We can ask how a given point in space is moving. We know its position with respect to time. Position will be denoted with a variable x. Right? The speed, the velocity v is the derivative of position with respect to time. And the acceleration is the derivative of velocity with respect to time. Right? Now, if the velocity everywhere in space is a function of both space and time, we can use the chain rule, and it says that the acceleration will be the change of velocity with respect to time, plus the change of velocity with respect to position, plus the derivative of position with respect to time. Okay. Or we can write this in vector notation here, right? The acceleration will be the change of velocity with respect to time, the acceleration in a moving reference frame, plus the dot product between the velocity and gradients of that velocity. Okay. And this is a quantity called the material derivative. The material derivative is a change of some quantity in a moving reference frame. Okay. Okay. And so we can pick any quantity here. We could have called this density, for example, right? I think all the pictures you will see, capital D is used for this material derivative, often called the convective derivative. And why are there two parts, right? There's two parts to this derivative. There's a time derivative, and then there's a part that depends on the velocity. And sometimes people call this the normal acceleration in the case of velocity. Derivative of velocity with respect to time is an acceleration. The second term people sometimes call the convective acceleration, because as you move from one place to another, the velocity changes, and your velocity, because the velocity is changing in that moving reference frame, you may be accelerating. So as an example, you may have a stationary velocity field that's not changing over time. But as you move through that velocity field, what's the first term if the velocity is not changing with respect to time? This will be 0. The second term is not 0, right? So even though the flow is steady, meaning it's not changing with respect to time, you may still experience accelerations because you're moving through a fluid where the velocity is changing in space. Okay. Anyways, this is called a material derivative. So one useful thing you can do with this concept now is there's another tool. Okay, right. So sometimes you might be interested in not how a quantity varies with respect to space and time in a moving reference frame, but how the integral of that quantity changes. Okay, so now V of t is the volume circumscribing this mass m here. And this volume is going to be moving with the fluid, right? And the volume may be changing with respect to time because of the mass is moving with respect to the fluid. And we would like to know how the integral of this quantity f is moving in that reference frame. So we'd like to take its derivative with respect to time, not just of f, but the integral of f over that volume. Okay. And there's this thing called the Reynolds transport theorem, which I'm not going to derive for you, that tells us how we take this derivative sign and move it inside the integral. Okay, and so we have a normal material derivative plus a little extra term that's the function times the divergence of the velocity. And that's called the Reynolds transport theorem. It's like the material derivative, but we have to take our integral with respect to time inside an integral that's over a volume that varies with time. But here's some useful things you can do with that. Let's revisit our conservation of mass equation, right? And we'll start with our statement right up here. Mass is equal to, by definition, the integral over that volume of rho dv, right? That volume v of t is moving with the fluid. So in that volume v of t, what's happening to the mass if we're neither creating nor destroying mass? It's not changing, right? So we should be able to take the derivative of m in the moving reference frame, right? Capital D of mass with respect to time. And what should that be equal to? In the moving reference frame. So in this blue box. How's m changing? It's not, right? So that if it's not changing, it means the derivative with respect to time, the material derivative, is 0. Okay, so we'll take the derivative of that mass, right? And here's where we use those useful tools. Where we want to take this time derivative, move it inside the integral sign. And so we use that thing called the Reynolds transport theorem. Okay. V of t is anything, so the only way for the integral to be 0 is for what to be true? The inside has to be 0 as well. Okay. And we get back to exactly the same equation we had on the board that's now hidden. Okay. Right, so here are a variety of different ways of simply writing the conservation of mass equations with the reminder, if density is constant, you get an equation that says the divergence of velocity is 0. Okay, questions about conservation of mass? Okay, conservation of momentum. What's momentum? It's mass times velocity. Thank you, Abby. Right? Okay. So that's momentum if you have a single object. But now, of course, we're in a fluid. It's moving it's moving in space, right? We integrate over some volume, density times velocity. That looks like mass times velocity, right? Okay, and that's our momentum. And conservation of momentum, or Newton's second law, says that force is equal to what in Newton's second law? Mass times acceleration, right? That's equivalent to the statement of conservation of momentum. Okay, right? Because if we take the derivative of momentum with respect to time, we get mass times acceleration. Okay. So this is very nice. This is our second law. We're conserving mass, we're conserving momentum, and we're going to conserve energy. This is still not a useful equation, right? We would like to be able to apply this to a geodynamics problem to interpret, for example, the blue and red images you saw earlier this morning. And so we're going to need to do a few other things to this equation to put it into a form that will be useful for us. And once again, I'm going to go to the blackboard and take you through this. I'm sure we have time. And I want you to interrupt and ask questions. And this time I'm going to cheat. I have a sheet of paper to make sure I don't forget too many steps. Okay. Everyone got these addresses? Okay. So let's take our volume. It's bounded by, we've got a velocity. We don't care about this anymore. You know the definition of a unit normal vector. Okay. And I will start by rewriting the statement of conservation of momentum that Bruce had on that slide. And it was that the change with respect to time of the integral over volume of density times velocity or momentum was equal to a set of forces that are acting on our volume. Okay. Yeah.
How bad is it if we messed up and didn't use the material derivative?
So bad. The question is how bad is it if we forget the material derivative? Yeah, so let's imagine we just if we didn't do it here, we would have something that looks like V times grad rho. So now we also have terms that involve spatial derivatives of V as well. So that's why my glib answer was so bad. You'd be wrong. And, I guess that's one of the first things you learn in calculus is the interchangeability of order in which you do things. But you can't do that because V is a function of time here, and you'd like to take a derivative with respect to time. So the order in which you do things matters. Yeah. Thank you. Okay, so what are examples of forces that might change momentum? Essentially, we're saying that we have a certain amount of momentum. The only way to change it is to apply forces to our volume. So what are examples of forces? Gravity is a good example. And so I'll just go ahead and write these down. So what's the gravitational force on that volume? Gravitational force looks like density times volume times gravity, right? So it's density times gravity integrated over volume. And I guess I should probably mention a bit about notation. If I put a line under something today, that means it's a vector. It depends on one direction. Later you're going to see two lines. That'll be a quantity that depends on two directions. We call a tensor. Okay. Is this the only force that will act on something? Gravity? Yeah, we could apply forces to this volume, right? I could take my hand and grab one edge and push on it, right? That's an additional applied force. Okay. And these are forces that are applied over the surface. So we'll let our surface be a function of time because this volume is deforming. And I'll just simply call these T. So what is T? This is a force per area, per unit area, normal to the surface. Okay, so this is a much better looking equation for our conservation of momentum, in that we're relating changes in momentum to forces that act throughout the volume. These are called body forces, and forces that are applied to the surface. Once again, though, I think you see a feature of this equation that looks similar to the one we just saw, in that we have a volume integral for two terms, and we have a surface integral. How do we get rid of surface integrals last time? We used the divergence theorem, right? So to make this into a form where we can apply the divergence theorem, we're going to let this force per unit area, T, be equal to the dot product between a second-rank tensor and the unit normal vector.
So, Michael, just to clarify, you said the lowercase t is perpendicular to the surface?
Yes.
So you're not interested in rotations of the body? Because t dotted with n actually gives you a vector that doesn't have to be perpendicular.
That's right. It does not have to. Yes. I think so. Ved said something that was great. Okay. So let me define what these stresses are. They're forces per unit area. I'm going to define what these stresses are. Maybe this will address what Ved was pointing out. Okay, and I'll define my coordinate system this way. Let's see, y up, x horizontal. And so what is these things called tensors? Are you going to talk about tensors in your lecture?
No, Steve Grant.
Steve is? Okay. Shoot. And I wasn't quite prepared to go into tensors in too much. Tensors are physical quantities that depend on two directions, okay? So I can write, for example, t. I'll write it now as t subscript. In the same way with a vector, we could have vi, right? In the x direction, where I represents the x direction, y direction, z direction. Tij would depend on two directions, right? Where the first direction would be the direction of the force, and the second direction, index, is the direction of the surface. Okay, and to illustrate that, I'm going to take this little box, right? Here's our coordinate system. And we have a stress, I'll indicate with this line, acting on the top surface, right? And I'm going to put two indices there. What should the indices be? What should be the first index? The force is acting in which direction? In the x direction. On a surface oriented in what direction? Okay, so now you have to wonder, how do you characterize the orientation of a surface? We've been doing it with a normal vector pointed outward from the surface. And so the subscript here would be t, x, y. Okay, we have another force acting this way here. What will the subscripts be? The force is in the y direction on a surface oriented in the x direction. Okay. Don't forget that picture if I erase it, because we're going to use it in just a second. Okay. So because we've introduced this, we've replaced vector t with this thing called the second rank tensor capital T. This now looks like t dot n over an integral over surface. We can use the divergence theorem, right, to convert that to a volume integral. And so I'm going to skip a step, and we know how to use the Reynolds transport theorem for the first term. This is a volume integral. We've just made this a volume integral with the divergence theorem. And so our equation now looks like derivative of rho v dt plus the divergence of rho vv is equal to rho g plus the divergence of t. And all of this was originally an integral over volume, right? I've just dropped that volume integral. Okay, so A couple things, right? I think we're in much better shape than where we started. We want an equation we can solve, right, to understand how the mantle's flowing. Okay, we know everything here. In order to solve a set of equations, though, right, there's a bunch of unknowns in an equation. What has to be true about the relationship between the number of equations and the number of unknowns? They should be about the same, right? Okay, they should be exactly the same is more correct. Okay, so let's go ahead and count up. How many unknowns do we have? Let's do something easier. Let's say start with how many equations do we have? Abby says 2. Nick says 6. This is not the hardest thing in the world to count equations, right? I will give you a hint. Let's also say that we know that mass is conserved. We'll count this as one equation. How many equations do we have here? It's an equation for the velocity, right? And velocity has how many components? 3, right? In a Cartesian coordinate system, it's Vx in the x direction, in the y direction, the z direction. So how many equations? 4. Okay. 3 plus 1 is 4. Okay. We will never finish on time if you don't speak up. But Barbara, I will finish on time, don't worry. Okay, how many unknowns? Velocity has 3 unknowns, right? So we're up to 3. Stress has how many? Many. It's a second-rank tensor. It's 3 by 3. 3 times... we haven't said why it's symmetric yet. 9. So 9 plus 3 is 12. Okay. So we're not in good shape, right? And the point of taking you through this and why it's so important is you're going to see why we have to introduce additional equations to make this a solvable problem. Because we've made no approximations yet, right? This is all good. Okay, so Barbara mentioned the stress tensor is symmetric. And how do we know the stress tensor is symmetric? There's a physical reason that we can argue on the basis of conservation of angular momentum. Let's put my finger in the middle of this box, right? And let's this stress in that direction, these are called shear stresses, is exerting a moment or a torque about my finger, right? That torque is equal to the length of this distance times that stress. Okay. So there is a torque exerted about my small finger. This other stress is exerting a torque as well, right? And what's the direction? It's in the same direction as the other torque, right? If these two torques did not balance exactly, what would happen? We'd have a difference in torque, and things would start spinning and go faster and faster and faster. And so the only way for those to balance is if Tyx equals Txy. What does that make T then? If Txy equals Tx, if Txy equals Tyx, the stress T is symmetric. Okay, if it's symmetric, then 3 of the components, I'm going to go ahead and just write this down. This is symmetric. So we've now lost 3 unknowns, and we're down to 9. Okay, so we're making some progress, right? But we still have 5 more unknowns than we have equations, right? And so this means that we have to do something else. And that something else is to introduce something we call a constitutive equation, or a constitutive law. And that law, you can already anticipate what the challenge is, right? Velocity has 3 unknowns. We have 4 equations, right? So there's not much else we can add. And so what we're going to need to do is to relate our stress T to quantities like the velocity, right? Okay. And so the example I will show you first is for something called a Newtonian fluid. And as I'm writing this down, I'll remind you that we have 2 lectures and 1 tutorial on this topic that we'll be talking about now, constitutive laws or rheological laws that relate stress to deformation. Okay, so more generally, we can break our stress into 2 parts. a part that's isotropic, that doesn't depend on direction. The symbol I is the identity matrix. It's a matrix that has 1s on the diagonal, 0 off diagonal. P is the average stress. Right, so it's equal to minus 1/3 the sum of the diagonals of the stress. Whoops, let me see, I'm changing notation. Okay. So we can take that stress quantity T, average the values on the diagonal. That's what we call the pressure. It's the average value of stress. If you've seen tensors before, you know that this is an example of something called an invariant. It doesn't matter what coordinate system you pick. The sum of the diagonals of the stress are always exactly the same. So we take our stress T, we subtract from it the pressure. We get something else we call the deviatoric stress. I'll use the symbol tau for now. And the deviatoric stress here is simply the actual stress minus the pressure, right? Okay, and this is where we introduce these things get complicated. We need to express our deviatoric stress in terms of a smaller number of variables, and it could depend on the speed the fluid's moving, the gradient of velocity, and so on. Okay. And the actual mathematical relationship between stress and how the fluid is deforming is what we call a constitutive law. So what we're going to do now is hypothesize that in our fluid, the deviatoric stress tau is proportional to velocity gradients. It's spatial differences in velocity that give rise to stresses. Okay. That's fine, right? It is a hypothesis, though, or a model, I should say, right? That this is what gives rise to stresses. Is this symmetric or not? Tau has to be symmetric. Does the gradient of any vector have to be symmetric? There's no reason why it needs to be symmetric, right? So what we're going to do is introduce something I'll call the rate of strain tensor. Strain is fractional deformation. Rate means a time derivative. And we want it to be proportional to velocity gradients, but at the same time it has to be symmetric. And so the easiest way to make something symmetric is to take this quantity, right? That's a second rank tensor, and add to it its transpose. Okay. What is the transpose? You take a matrix and just flip everything about the diagonal. Okay. Right. And so if we take everything, flip it about the diagonal, and then add it back to itself, the sum of these two tensors has to be symmetric. Okay. And the sum of those two quantities is what people call the rate of strain tensor. Okay. And then if we do this, I'm going to erase this equation here. We're going to assume the stress is proportional to the rate of strain tensor. We can make this equal to, we're assuming it's a linear relationship, right? The simplest linear relationship, it turns out, between two second-rank tensors involves a fourth-rank tensor. How many quantities are there in a fourth-rank tensor? 81. But the good thing is we don't have 81 parameters in this problem. And for a variety of arguments that I'm not going to go through, and maybe the seismologist will, or not. You're just going to write it down? I'm just going to write it down too. How about that? Through a variety of arguments that would take at least 45 minutes to go through, you can show that there are only two independent parameters, so that our stress T is equal to minus P plus a quantity that I called in my notes lambda, divergence of velocity. So again, this is the isotropic part that relates the average stress, that describes the average stress plus 2 times eta times the rate of strain tensor. So we have two new material properties that enter. This is called the bulk viscosity. The second one is called the shear viscosity. Okay. And those are the two material parameters that relate, finally, how things are deforming, right? E describes the deformation, right? The spatial gradients of velocity or the divergence of velocity to the stress. Okay. How many unknowns do we have? This was the point. We have 3 unknowns for velocity, 1 unknown for the pressure, and we have, so what's 3 plus 1 is 4, and we have 4 equations, and we're good to go. So if we substitute this definition of stress into the equation that I had written on the board that I erased here that had the divergence of the stress, and we assume that the divergence of velocity equals 0, we have an equation that looks like density times derivative of velocity with respect to time plus u dot grad u is equal to density times gravity plus mu spatial derivatives of velocity. Okay. Nick? That's an I. Yeah. Sorry. Okay. And this equation, this is a famous set of equations. It's called the Navier-Stokes equations. And it just describes the flow of a fluid with the assumption that density is constant in space and time. Okay. Okay. Any questions? Okay. Torsten?
Just note that this is for isotropic mechanical behavior. If this has volume, it's going to come back to fully anisotropic, then it's 21 independent in that C thing, right?
That's right. So Torsten raised an important question. This constitutive law is for what we call a Newtonian fluid. This is a mathematical definition of what we mean by a Newtonian fluid. And if we want to relax some of the assumptions, for example, we said this fluid is isotropic, no direction dependence. We have to make these equations, of course, more complicated with more unknown material properties, but not necessarily more unknown physical quantities, right? As long as we can relate everything to the velocity, which in this case centers through E, we still have the right number of equations and right number of unknowns. We just have lots and lots of material properties. Okay.
We have a couple of questions.
Jessica?
The bulk viscosity and shear viscosity, are they actually bulk modulus and shear modulus?
So
What have we got?
I meant the U here was a V. Everything here is for velocity. But there's a mathematical similarity between shear moduli and bulk moduli and shear viscosity and bulk modulus. You might notice in that famous equation I called the Navier-Stokes equation, there was no bulk viscosity. Why is that? We assume that the divergence of velocity is equal to 0, and if you look at our equation for stress, if the divergence of velocity is 0, it doesn't matter what the bulk viscosity is. Right? Bulk viscosity of liquids or in fluids is very poorly known and measured because most liquids and fluids are pretty close to incompressible. So it's not an easy quantity to measure. Okay, so
Michael, there should be a pressure gradient term in that family equation.
Oh, for sure. That's super embarrassing. Okay, I'm not going to lift up the board. The right-hand side of the equation, it was rho g. There should be a term that looks like gradient of pressure. The gradient of pressure is super important because it makes everything happen. Okay, conservation of energy, we do the same thing. The thermal energy inside some volume is density times specific heat times temperature. We integrate over volume. That's the amount of thermal energy. It will change if we lose heat across our boundaries S. It can change if we add or destroy heat inside that volume, right? So exactly the same concept. We conserve a quantity, we let things enter and leave, and change it in the volume. We can convert this to a volume integral using the same things we had before. And last thing to note, what governs heat transport across a boundary is governed by Fourier's law that says that the heat flux Q is equal to a thermal conductivity times a temperature gradient.
So R would include radioactivity and viscous heating?
Okay, so this is a bit tricky. R, going back here, This integral over volume of things that produce heat. R, as written here, includes radioactivity. Some of the viscous heating enters through on the right-hand side, on the left-hand side, actually. This is a change in the moving reference frame. It will give rise to a velocity on the left. And divergence of velocity give rise to volume changes, which give rise to temperature changes. Right? If things expand, they cool. If they contract, they warm up. And so there are a number of places where you can get volumetric changes in temperature by producing heat by radioactivity or by fluid motion as well. Okay. And so we end up then with this set of equations: conservation of mass, conservation of momentum, conservation of energy, with a number of assumptions and approximations built in. In particular, we're going to assume, as written here, that density is equal to a constant. Okay.
How good is that approximation?
That density is constant? It's not a terrible approximation. So we can relax successively some of the approximations that we have made here. For example, in our conservation of mass equation, we might assume that changes of density with respect to time are zero, but we'll let the divergence of rho u be equal to zero. That's called the anelastic approximation. Some of you may know this is a wave equation, right? It's a first-order wave equation, and that time derivative can cause lots of mathematical or computational problems. So if you filter that out, but let density vary in space, then that's called the anelastic approximation. Maybe something else we'll point out. Okay, so as mentioned earlier, Quentin showed this equation earlier, so I'm not going to explain in great detail. Density changes with respect to temperature, right? And the rate at which density changes with respect to temperature is what we call the coefficient of thermal expansion. And it gives rise to buoyancy forces. Light things go up, heavy things go down. So we can't ignore it in the momentum equation, right? Otherwise, we wouldn't have convection. We wouldn't have light things going up and heavy things coming down. But we might say those variations of density are small, and so we might still retain the approximation that those density variations are small. I think for most problems, it's not a bad approximation. It's not very good in what we call compressible fluids like gases, especially if they're going very fast where we get shock waves. Okay. Okay, and then of course to solve equations we need boundary conditions, and I'll skip this, and when it comes relevant I'll tell you about boundary conditions. Okay, so a little bit about the next topic that Bruce wanted to cover is these things we call dimensionless numbers. Okay, and there are two ways to think about this. Actually, I will do one way on the board, and then I'll show you the way on the slide. And this gives me a chance to fix my egregious typographical error. And that should be a minus sign. Okay. So we have an equation written down there that describes conservation of momentum, where this term here is the derivative in the moving reference frame with respect to time of velocity. So we might have a flow problem, and I think the example that was on the slide that Bruce had was flow between two parallel surfaces. Right. Fluid is moving left to right with some speed. He called it V max. We'll let L be the dimensions over which this velocity is varying. And you might wonder, well, lots and lots of terms in the equations, are they all important and are they all dynamically important? So let's go ahead and estimate the order of magnitude of each of these terms. So on the left-hand side, in the governing equations, this was the mass times acceleration term, right? We said mass times acceleration is equal to a set of forces. So let's estimate the magnitude of mass times acceleration. It's equal to density. Capital O means order of magnitude. So we're going to estimate what's the order of magnitude of these forces. It looks like density of the fluid times V max, okay, divided by some time scale. How do we get time? Distance is speed times time. So time is a length divided by a speed. So L over V max. So that looks like density times maximum velocity over length. That's an estimate of the magnitude of the terms on the left-hand side. What's the magnitude of this term over here? Shoot. I'm going to call this eta to be consistent with Bruce's notes. Okay, it's the thing called the shear viscosity. That looks, the order of magnitude is shear viscosity times the maximum velocity divided by a length squared. Okay. So if you would like to know for a given problem how important different terms are, all you have to do is compare them. Okay, and so we will do this. We're going to compare density times Vmax squared over length divided by viscosity times Vmax over length squared, which looks like density Vmax length over viscosity. Okay. It's the ratio of the magnitudes of those two terms in the governing equations. What are the units of this expression on the right-hand side? It has to have no dimensions. We're comparing, in any equation, every term has the same units, right? So if we compare two terms in that equation, they have to have the same units, hence the ratio has no units. And so this is an example of a dimensionless number. It's got a special name. It's called the Reynolds number. And it's representing something real, something that's physical, right? I told you the left-hand side describes the mass times acceleration of the fluid. That's a measure of how much inertia it has, right? It's moving at some speed. How much does it want to keep moving at that speed? So it's equal to the ratio of inertial forces to, okay, what's this term describing? The importance of viscosity, right? So we'll call this viscous forces. Okay, and the handy thing is, let's imagine we have a flow where the Reynolds number is really small. What can we do? Reynolds number much less than 1. What does that mean? Inertial forces are not important, right? Compared to viscous forces. So we can go back up to our governing equations on the left-hand side and throw all this away and not bother solving for it. Okay. So there are two reasons we use and introduce dimensionless numbers. One, it allows us to tell how important different terms are, whether we can neglect them or not. And from the governing equations, we can do a variety of interesting things mathematically at that point. The second thing is it also gives you insight into what the solutions will look like. Right? If we know that in this equation, the only variable is this Reynolds number, it tells us that if we change the speed by a factor of 2, that's equivalent to changing the viscosity by reducing the viscosity a factor of 2. Everything's the same. So you don't need to solve a bazillion problems. You solve one problem for this given Reynolds number, and that tells us the relationship between changing length, changing speed, changing viscosity. For the mantle convection problem, it would be telling us the relationship between, if you change the viscosity by a factor of 10, that's equivalent to changing, well, it's a different problem. Coefficient of thermal expansion, for example, by a factor of 10. Okay. And so this is the beauty and value of these dimensionless numbers you will see repeatedly, is they tell us the relationship between forces, but also how the fundamental variables in the problem are interrelated as well. And so there are a variety of ways we can figure out what these dimensionless numbers are from our equations. We can introduce things we call dimensionless variables. Here, x prime will be the actual position divided by some length scale. We'll call it r. We do the same thing for the speed. We do the same thing for the time. We substitute those new variables into our governing equation so that every term that has a little prime here, the triangle should have a prime. Those have no dimensions. All the quantities that have real dimensions get lumped together in these things that are called dimensionless variables. And you saw the Reynolds number on the board, right? It was equal to the maximum speed times the length divided by viscosity times the density. Okay. And so you can derive them formally from the governing equations or just compare different terms. Okay. So next problem is the convection problem, and this is where you will see another one of these dimensionless numbers. right? So what are we trying to do here, right? We've just derived the equations for conservation of mass, momentum, and energy. We'd like to know if we have a fluid, is it going to convect? So we have a layer of fluid, hot at the bottom, cold at the top. There's a temperature difference, delta T, across the layer. It's got a thickness L. Okay. So like on the previous slide, we can introduce these dimensionless variables. We just say our temperature T is equal to T prime is equal to the actual temperature divided by the temperature difference. And every time we go into our original equations, replace all the temperatures with T prime times delta T. And we do that with all our variables. And so the three equations you saw before reduce to the three equations written down here. Okay. And every term or every expression here that has little primes has no dimensions. And all the variables that you made them dimensionless with enter through these groupings that are, again, physical ratios of physical quantities that have no dimensions. Okay. So let's think about what these are. What happened to the Reynolds number that we had before? It's gone. We have a new one called the Prandtl number. Okay. We have another dimensionless number called the Rayleigh number. Okay. So the thermal convection problem we've set up here has only two dimensionless variables, the Prandtl number and the Rayleigh number. I'll give you a physical interpretation of them of the Rayleigh number in a second. First, though, for the mantle, let's estimate some of these numbers, the Prandtl number. What's the viscosity of the mantle? It's 10 to the 21. We'll do everything in SI units today. 10 to the 21 Pascal seconds. Thermal diffusivity. So you haven't seen the symbol defined yet, right? Bruce skipped over defining it. It's thermal conductivity divided by density times specific heat capacity. This is 10 to the minus 6. So 10 to the 21 divided by density divided by 10 to the minus 6 is 10 to the 24. And it enters as 1 over 10 to the 24. What's the order of magnitude of all these terms as when we've made them dimensionless? They're close to unity, right? So every term groups you see here is about 1. These are multiplied by 1 over 10 to the 24. So what can we do to the second equation? We get rid of all the left-hand side. They don't matter, right? And this turns out to be super convenient because the beauty in the Navier-Stokes equations, or the ugliness, depending on your perspective, is this nonlinear term u dot grad u. Okay, so what we'd like to do then is if we have this layer of fluid hot at the bottom, cold at the top, we'd like to know, is it going to convect? Right? Okay, and why might you expect it to convect? Right? If there's no fluid motion, how is heat transported? By conduction, and conduction takes heat from the hot place and sends it to the cold place. But because we have a difference in temperature, we're going to change density. Right? Where's the light fluid in that box? It's at the bottom, right, where it's hot, because as you heat things up, the density goes down. So we also have something that intuitively you might expect is unstable, in that we have light fluid sitting underneath heavier fluid. And that's a geometry that's prone to undergo convection, where light things go up and heavy things go down. And so we'd like to know whether that's going to happen. So the way in which people figure out whether convection should happen is by doing something called a stability analysis. And the idea is pretty simple, right? If there's no flow happening, right, again, we said heat transfers by conduction, and we know what the solution is. Temperature is going to vary linearly as we go from the bottom to the top. And now what we're going to do is disturb that solution just a little bit. We'll let the temperature T fluctuate within the box. And then we can ask whether those fluctuations, those perturbations, get bigger and bigger, or do they disappear and go back to the conductive solution. And so mathematically, you let your temperature be equal to the solution to the conduction problem. It varies linearly with respect to depth. You let it vary in space, x, y, z, and you assume it varies in time, and it has an exponential dependence on time. If the solution is unstable, the conductive solution is unstable, sigma is going to be positive. If it's positive, what happens to the term on the right-hand side? It grows with respect to time. If sigma is negative, it decays back to 0, and the solution then approaches your conductive solution. Okay. And so the way in which people figure out whether convection should happen is by figuring out whether the conductive solution is stable or not, to perturbing the temperature. Okay, and so the only dimensionless number that characterizes this problem is this thing called the Rayleigh number. I'll describe it physically next. And we can change the Rayleigh number going from small to big. Right? It's the only one thing that can vary, and ask whether convection happens. And so plotted on the right is the solution to this problem. B is the thickness of the layer of fluid. Lambda is the horizontal dimension of the flows that are induced. And the vertical axis is how big this Rayleigh number needs to be for convection to happen, where unstable indicates that convection is going on. Stable means the solution reverts back to the conductive solution. Okay, so physically, though, what's going on is a competition between two processes. We're producing buoyancy at the bottom because it's hot, and light things want to rise, but we're also transferring heat at some rate as well. And if conduction is efficient enough, then convection will not arise. And so this gives rise to a physical interpretation of the buoyancy of the Rayleigh number. And there are physical interpretations of all these different dimensionless numbers. And the argument and derivation here was first introduced to me by Rick O'Connell, who was one of the co-authors on the first paper to discuss the relationship between seismic anomalies in the lower mantle and the geoid and plumes and so on that Barbara mentioned earlier. Okay, so we have a region with dimension L, right? It's hot. It's got a temperature anomaly, delta T, that gives rise to a density anomaly, delta rho, right? And we can estimate how fast that blob is going to rise by comparing the order of magnitude of terms in the momentum equation. And it looks like density difference times gravity times its dimension squared divided by the resistance, which is coming from viscosity. So the time scale for this blob to rise, right? The relationship between length, time, and velocity, distance is speed times time, right? And so we can get a time scale for it to rise. It looks like a velocity. It looks like a length L divided by a velocity. So that's how fast we're carrying heat, or we're carrying buoyancy because things are light and they're rising. We can compare this with the time scale to transfer heat by conduction. Do we have the equations? Okay. If we're only transferring heat by conduction, it says that the change of temperature with respect to time looks like a thermal conductivity times a second spatial derivative of temperature. Right, that's an equation called the diffusion equation. And in all diffusion equations, time scales look like a length squared divided by a diffusivity. Okay, so that's a conductive time scale. We can compare the ratio of those two time scales, right? And we get a quantity that looks exactly like the Rayleigh number you saw before. So one interpretation, physical interpretation of the Rayleigh number, it's a comparison of the time scales for two different processes. To transport heat by conduction compared to the time scale over which you transport heat by the fluid circulating. Okay. And so maybe it's not surprising the Rayleigh number has to be big enough, right, for advection to matter, and that occurs when conduction is unable to transport the heat fast enough. Okay. I'm going to go very quickly through this concept called boundary layers now, because we just said that if we have the conductive solution and temperature varies linearly with respect to depth, if the Rayleigh number is big enough, the fluid will start to convect. Hot things go up, cold things go down. And so the actual temperature distribution we see looks like the picture on the right, where heat is conducted through a thin layer at the top. It's nearly isothermal in the middle because fluids are rising fast and sinking fast and there's no heat conduction. And all the heat conduction is occurring in these thin layers at the top and the bottom of this box we call boundary layers. Okay. And so there's two regions, in fact, that we see in convective regions. One where heat conduction doesn't matter very much, another where heat conduction dominates. And that's what we call boundary layers. And boundary layers turn out to be the key for understanding how and why convection occurs. Okay. So to understand how and why this happens, let's imagine we have a hot fluid. It's at some temperature T everywhere. And the top is cold, right? Heat is going to be conducted through this boundary layer, right, where we have a temperature gradient to the surface. If we have absolutely no flow happening, so you just take a hot layer of fluid, you make the top cold, it starts to cool. this boundary layer where heat has been transferred by conduction is going to move downward with respect to time. How fast does it move down with respect to time if all heat transfer occurs by conduction? In a diffusion problem, remember we said lengths and time are always related, right? Because we have a time derivative balancing a second spatial derivative. And so lengths increase like the square root of time with the constant of proportionality depending on how easily the fluid can conduct that heat. Okay. So we have something that's almost isothermal that represents our hot fluid. We're losing heat to the surface. This boundary that separates the part that is cooled and the part that is hot is moving downwards. And so its thickness is increasing with respect to time, right? At a rate that scales like the square root of time. And eventually, this boundary layer, this region where heat has been lost by conduction, gets thick enough that it becomes gravitationally unstable. Right? If we go back to our definition of Rayleigh number, which I didn't go into in great detail, it had a length in it. Right? The Rayleigh number scaled like the length cubed. So if we take a layer of fluid and make it thicker and thicker, what happens to its propensity for convection? It goes up, right? The thicker the layer of fluid, the more likely it is to convect. And what have we done by making our boundary layer get thicker? We've increased the propensity for that boundary layer to convect as well. And so we can now ask the question, how thick does this boundary layer need to grow by conduction so that it too becomes gravitationally unstable when it reaches the critical Rayleigh number for convection? Right. Okay. And so this we can figure out how big this thickness needs to be to reach the critical Rayleigh number where it starts to convect. Okay. And I messed up with my time management, and so let's see. Here's what we're going to do with this, right? I know I lost 15 minutes at the beginning, but we need to eat lunch. And so lunch is more important. So, okay. Once this boundary layer becomes gravitationally unstable, it's going to sink downwards. And if you remember going back to the very first slide I showed you, we had things going down and things going up that were very thin and narrow, right? And these are manifestations of this boundary layer becoming unstable, sinking from the top. There's an analogous boundary layer that's growing by diffusion from the bottom, becoming unstable and rising. And that describes the first order, the convective patterns we see. It's governed by local processes that happen in the boundary layer that represent an interplay between two different processes, transferring heat by conduction, things becoming gravitationally unstable, and then transferring to a regime where advection dominates and heat conduction doesn't matter much. And that's the bulk of the fluid. So we know how thick our boundary layer is when it becomes unstable. We can now calculate how much heat is coming out of this layer of fluid, right? The heat flux Q. Right? It's by definition the thermal conductivity times the temperature difference across the layer divided by the thickness theta. Okay. And we can introduce this thing called, we can compare how much heat is conducted out of a convecting fluid, transferred out of a convecting fluid, with how much heat would have been transferred if no convection was happening. Okay. And so this quantity is called the Nusselt number here. This is your fourth dimensionless number, Nu. It's how much heat is carried by convection compared to how much heat would be conducted if no convection was happening. If no convection was happening, right, the heat transfer looks like thermal conductivity times the temperature difference divided by the layer thickness, right, if only heat transfer occurs by conduction. The amount of heat transferred by convection is equal to, again, thermal conductivity times the temperature difference, but now only half the temperature difference because we're going from the median temperature of the fluid to the surface, divided by the thickness of that thing we called the thermal boundary layer. And the ratio of those two quantities we called the Nusselt number. And notice it looks like the layer thickness divided by the thermal boundary layer thickness. Okay. And so what's illustrated here is since we know the relationship between the thickness of our thermal boundary layer when it becomes gravitationally unstable and this Rayleigh number, right, this was what we just derived, we can derive an expression that tells us what the Nusselt number is, the heat transfer, as a function of the Rayleigh number. And what's the prediction? It should scale like the Rayleigh number to the 1/3 power. Okay. On the left is a plot of Nusselt number as a function of Rayleigh number based on experiments done in liquid helium at the University of Oregon over, that's about 11 orders of magnitude. There's a best fit to that data. And what's the exponent? It's 0.309. Is that 1/3, like the theory? It's pretty close. I guess if you're a geochemist, you'd say you're great, right? If you're a dynamicist, this is very, very unsettling. It means there's something else going on, right? Because 1/3 doesn't overlap with that, right? Okay. And so there's additional physics and processes that are hidden in the simple treatment where we're saying the boundary layer becomes gravitationally unstable, giving rise to an expression we can use to determine heat flow. I was going to do this on the board instead. These are three.
Is it more like 1/3 if you restrict the Rayleigh number interval, say just up to 10 to the 7 or 10 to the 8? In other words, part of that.
Okay, so the question is there a region where 1/3 in fact characterizes things? There's a huge community of field who've devoted entire careers to understanding what's going on here. There are different asymptotic limits governed by different types of physics, including, for example, theory that says it could scale like 1/3. Other models for how turbulence works and the relationship between small and big scales that give rise to a 2/7 scaling. So it really comes down to the details that relate small scale processes to the large scale. And as we've treated this problem here, we said there's only two scales: the thickness of the thermal boundary layer that becomes unstable, and the thickness of the whole layer that we assume is thermally well mixed and has a single mean temperature. And so it's, in fact, the richness of these physics comes down to the interplay between different scales that have been hidden. Since these slides are posted, 3 homework questions. How thick is the layer when it becomes unstable? How long does it take to become unstable? Why are these 2 homework questions? Because these are things you can compare with observations. You know something about the age of the lithosphere on the surface of the Earth. Hopefully it matches this time, right? Otherwise, this model is not a very good description of the Earth. This is the most interesting question, I think. How does the heat flow depend on the thickness of the mantle? And you will come up with an answer that I think will surprise you if you haven't done this before. And so when you get an answer, please come talk to me, and we'll have a good chat. Okay, so very briefly in the last 2 minutes, this picture we went through, we have a uniform fluid with uniform properties, and the only thing driving flow was temperature. Hot things are light, they go up. Cold things are dense, they go down. The real Earth has many complications, and it's these complications, in fact, that we're mostly trying to understand over the next several weeks that explain the richness of the geological record and geodynamic processes. And I'll take you through where some of these complications come from. We know that the Earth melts at the surface, right? Hot upwellings pass over the solidus and start to melt. And we may start with alert light, right? When it melts, we extract the salt to make the oceanic crust. We're left with something else. Notice these 3 numbers. These are all densities at the same temperature. And the treatment we went through assumes the density is the same at the same temperature. Here, because of convection that gives rise to melting, we produce things that have different densities owing to composition. And in fact, if we go back in time where the Earth may have been hotter, the thickness of the basaltic crust in blue and the residuum produced by melting goes up. And remember, both of these components of the Earth are less dense than the underlying mantle. And so there's a compositional effect on buoyancy that in the real Earth matters, and in a non-trivial way. Right? It's not just thermal convection governing heat transport in the Earth, but that thermal convection gives rise to variations in composition. Other reasons we might have differences in density were highlighted in both presentations this morning, that we have these large low shear velocity provinces at the base of the mantle and other structures within the mantle that are most easily explained if we have a difference in composition, which gives rise to a difference in density, superimposed on the flows caused by differences in temperature. And so to summarize from Bruce's last slide, right, instead of summarizing what we've learned, a set of questions, right? How good is our theory of mantle convection? And by this, I think he really means we can write down equations that describe exactly all the conservation laws. analytical treatments and mathematical treatments of those equations typically involve approximations so that they become more treatable mathematically. If we would like to extrapolate back in time, this is sort of what I skipped. We have some challenges to explain constraints on heat flow and the temperature in the past. We haven't said anything about boundary conditions yet in our treatment of boundary layers, in particular the size of plates. Equally important is that plates are different mechanically from the underlying mantle. They're not Newtonian fluids. And Magali and others will talk about rheological effects that enter into the dynamics that you were introduced to today. And so probably the best way to think about the equations you saw today and the boundary layer analysis that we went through too quickly is that this is a zeroth order treatment of mantle convection. Light things go up, heavy things go down. And the Earth gives us a greater range of complexity through differences in composition and a more complex rheology than a Newtonian fluid that makes the problem much more interesting and keeps us busy. And so I regret that Bruce was unable to come here but to give his presentation. But summary of what we intended to cover today, I'll post all these slides so you can read some of the notes. 3 homework questions that shouldn't take you more than 10 or 20 minutes, I think, and the last of which you'll find intellectually rewarding. Thank you. If you cool a fluid, it becomes more dense and it sinks. Red is hot, blue is cold. You can see regions where the mantle is rising, places where it's sinking. Right? Very simple description of what we call thermal convection. And to leading order, this should characterize what goes on inside the Earth, where the inside is hot and the surface is cold. I am not Bruce Buffett. These lecture slides were prepared by Bruce Buffett, and regrettably, he entered the hospital this weekend. I think he's okay, but I have not heard an update, and so I'm presenting these slides and this topic on his behalf. So please bear with me. But on Earth, we have plate tectonics, right, as a product of mantle convection. If we look around our solar system, in fact, we see different ways in which mantle convection operates and affects the surface. This is Jupiter's moon Io, the most volcanically active planet in our object in our solar system. Each of these things are places that have recently or are currently actively erupting. Rather than having plate tectonics, heat and mass is delivered directly to the surface. We see convection everywhere we look. Right? On the left is a rising cloud in the atmosphere. In the oceans, we have convection driven by variations of density. All convection is caused by variations of density, where the density changes originate from both changes in temperature as well as salinity. The contours you see here, I think, are differences in density relative to some mean density. This is a cross-section through the ocean. We see this layer of dense water sinking to the base of the ocean to drive and participate in the global ocean circulation. Convection in the sun. What you're seeing here is the influence of convection on Earth, on the magnetic field of the sun. These things are called granules. They're about 1,500 kilometers across. They last for 8 to 20 minutes, but convection once again. And the reason you have these 3 different pictures to go with the picture of mantle convection on Io earlier is that they're all manifestations of things going up because they're light, dense things sinking, but influenced to variable degrees by the importance of inertia, rotation, or magnetic fields. Geodynamics lecture number 4 is going to cover the E equals mc squared. That's a conversion of mass to energy. We will not worry about those complications. And to derive an equation that says how mass is conserved, let's take this volume and think about how much mass is leaving that volume at a given point on the surface. So let's pick a little surface here. Right. Why would mass be leaving that volume at that point? There's something else I need to draw in this picture. Right? We don't have a static blackboard, a static fluid. It's moving. Right? So we're going to have fluid moving through this region. In the notes that Bruce prepared, he uses the symbol V for velocity. If you see a U on the board by mistake, that's the same as V. Okay. So at this point here, are we going to have, do we have mass transferring, moving across that interface? We do, right? Because we have a speed, right? This fluid that's moving with speed, velocity V, is carrying mass across that interface. The mass flux per unit area is going to look like the density of the fluid moving across that surface times what? Times the velocity, right? That's telling us how fast mass is moving across that surface. Is that completely right? What happens if the velocity is perpendicular to the boundary? Parallel to the boundary. There's no mass flux, right? So the mass flux at any point is the dot product, right, the projection of the velocity onto the normal vector. Okay, so let's write down then the net flux of mass out of that volume V. And when I use the expression flux, that means mass per unit time per unit area. Net flux. Okay, so at any one point, right, the mass flux is rho v dot n, right? And if I'd like to know what the total is across out of this whole volume V, I just add up this flux all the way around the boundary, which is the same as integrating over that surface S. Okay. So that's how much mass we're losing or gaining depending on the nature of that velocity field. If we have mass leaving this volume, what happens to the mass inside the volume? It has to go down, right? So the mass inside that volume is equal to, what's the total mass inside that volume? Mass is what? Volume times density, right? But our density can vary with respect to position inside this volume as well. So to determine what the mass is inside that volume, we're going to integrate density over that volume, right? That's the mass inside the volume. And if we'd like to know how it's changing with respect to time, thank you. So we're going to integrate with respect to volume the density to get the mass. And this is a flux of mass, so how it's changing with respect to time. So we're going to be integrating the change of density with respect to time over that volume. And I'm going to put a minus sign in front of this integral. Why a minus sign? Right. If we're losing mass so that this is decreasing, the average density is going to change, right? Okay. So that's very nice. It's a statement of conservation of mass. Any approximations or assumptions? We're the quietest group of people for a Monday morning ever. Density could be a function of time, right? We're taking a derivative with respect to time. It can vary in space. We've made absolutely no assumptions or approximations. So this is great. We have a statement of conservation of mass. It's a little bit ugly, right, in that we have an integral over a surface, we have an integral over a volume. But there's a useful trick, hopefully you've seen at some point. The integral of something, dot product a unit normal over a surface, can be converted using the divergence theorem into a volume integral. And so this equation here can be written as the integral over volume of the divergence of rho v. So Ved just asked me a question, can people interrupt me with questions? And the answer is yes. If you get a microphone, that's great. If not, I will repeat the question so it's recorded for posterity. Thermal convection is the engine that powers geological activity. And on the Earth, the most obvious manifestation of thermal convection in the interior is the operation and existence of plate tectonics. This is Geodynamics 1, the basics of thermal convection. We have 3 goals today. The first is an introduction to the governing equations, and I will try and derive at least 2 of them for you. Second, why does convection occur? To do this, we will understand how we transition from a planet that transfers heat by conduction to one that undergoes thermal convection. And to end, and very briefly, I'll outline some of the complications to this basic picture of thermal convection driven solely by variations of density produced by variations of temperature. And it's those complications, in fact, that produce the great richness and cause us problems that were highlighted in the 2 presentations you saw earlier this morning. Okay, we're shortened by about an hour, by 17 minutes, and so I will do what I can to stay on time because we have lunch next. First, though, it's good to ask, why are we bothering to do this? Why do we care about mantle convection and how the mantle flows? And can we keep the lights on? I'm going to use the blackboard, Quentin. Thank you. The equations that we will be deriving and looking at today provide the basis and a starting point for solving on a computer or analytically for the flow inside the Earth. Right? And we will use the solution to this flow and the insights from those equations to interpret observations that we obtain from seismology or constraints from mineral physics. You will see in Geodynamics 3 by Torsten how we can more formally integrate observations with these equations to say something about the inside of the Earth as well. Okay, so let's begin with this picture. This is an example of a computer simulation of mantle convection. It's a solution to the equations we will be deriving in just a minute. It's a cross-section through the Earth. The bottom is hot, the top is cold. If you heat up a fluid, it becomes less dense and it rises, effects of rotation. Geodynamics lecture number 6 will add to this magnetic fields. So they will worry only about balances, flows that represent a balance between buoyancy and viscous forces. And let me remind you to interrupt and ask questions anytime as you have them. And that includes about notation, questions about notation, the mathematics, or of course the physical concepts. So here's our objective for the next hour, including questions and discussions. We'll begin with a brief overview of the governing equations, their origin, and some of the approximations that go into them. I'll introduce you to the concept of a dimensionless number and why we care about them and what we use them for. And I will try and remember to keep a running list of the dimensionless numbers on the board. And there's a reason for that. Very briefly introduce to you how we determine whether a system should convect or not, a way of describing a convecting system with something called the boundary layer model, and how we apply these boundary layer models to think about thermal evolution. Okay, so let's start with an equation that describes conservation of mass. And the equations that describe convection, for all those pictures that I showed you earlier, including the mantle, is a set of equations that describe conservation of a number of fundamental quantities: conservation of mass, conservation of momentum, and conservation of energy. And thermal convection is the product of solving that set of equations. So let's begin with the statement of conservation of mass. We're going to imagine we have this blackboard's a big fluid, right? We've got some volume inside this fluid. I'll call it V. It's bounded by surface area S. And to characterize this surface, we'll define a quantity we call the unit normal vector n that's normal to that surface. And what does it mean by unit normal? It means that the dot product of the unit normal, or the magnitude of this unit normal vector, is equal to 1. Okay. So the statement of conservation of mass says that we're not going to create mass or destroy mass. This is a great approximation for what we care about. Some of you know